Welcome back to class, everyone. Hello. Another wonderful day in the land of geology. I don't know why, because my cat still kept me up last night, but I feel a little bit more rested than yesterday. There was almost a disaster. Not a real disaster, but a work disaster. So I plugged my phone in at night on my nightstand, and I listen to what I call sleepy time music, and it's literally just like a noise track. In fact, here I can pull it up because it's on my phone. But it's like an 8-hour YouTube video, and then I found a program to download the video. But it's just like ambient noise, so it's not even like music. It's just like random weird noises. Yeah, just for 8 hours. Which helps me sleep. It helps like drown out all the noises.
Have you ever gotten an ad in the middle of it?
No, because I downloaded it from YouTube, so not online, and it's just the actual 8 hours of music. Because on my phone, like, I guess if you have the YouTube app, you have to have it open. You can't watch like YouTube on like Chrome. But if you have the YouTube app, it will not continue to play if you lock your phone and it closes. You have to have it open and the screen on for it to play. So yeah, I was like, I'm not gonna do that. So I downloaded it. But anyways, last night I guess my cats are like being crazy maniacs like they are at night for whatever reason, and somehow like unplugged my charger from the wall. And so all night my phone's playing music and draining battery down. And luckily, when the alarm went off this morning, it was at like 2%. But like had they unplugged it a little bit earlier, it would have died and the alarm wouldn't have gone off. And then I woke up and I was like, I asked my wife if her alarm was set, and she was like, no. I was like, oh, that was almost a problem. So luckily, I'm here and not late for work. So I don't think I've ever really been late to work except for the day I got in the wreck. So yeah, yeah, that's okay on that day. It wasn't my fault. Somebody else hit me. So let's see. I think we're good. Yeah, we have one person on quarantine. Hello, sorry you're on quarantine. Yeah, I got like 4 people in my classes on quarantine. That like the emails just kept coming last night. So everybody, make sure you're wearing your mask correctly and washing your hands. Although I guess all those people got possibly exposed at lunchtime, which is again why I don't eat lunch with the rest of the teachers in the teachers' lounge. Because as lucky as we've been, and we haven't had a lot of cases, going and sitting next to somebody for 20 something minutes with my mask down while we all eat and talk is not something that I want to do just yet. And I know, I'll say this on YouTube, I know the other teachers make fun of me. They're like, Bailey's all still worried about this. Like there's another teacher that's having a pool party soon, and it's not her first pool party this semester. And then she'll stand in the hallway and like yell about things. It's like, you have pool parties and you go to Buffalo Wild Wings with the other teachers. And those two things don't fit in the same sphere. So I'm being safe. Hello? No, I thought she was quarantined. Okay, no. Yeah, she's not here. Okay, bye. Making sure quarantine student was quarantined. So, if you're still at home, and I don't know, I thought that was interesting because they literally just yesterday sent out the email to the at-home students like, hey, you got to come back by November 2nd because we're not doing the online stuff anymore. And then we get a case and a bunch of people have to get quarantined. So, yeah, there's that. All right, let's actually get started on the earthquake stuff. So yesterday we left off with surface waves and body waves. The surface waves stay along the surface. The body waves go through the actual interior of the Earth and actually travel a lot faster. So these are our waves, and you'll see this on the lab. I don't know if I mentioned this in y'all's class yesterday, but I kind of realized it in the last class. I think I did mention it in y'all's class. we don't have to do this lab immediately. We have several of the next chapters that don't have labs at all. This earthquake lab is really nice. And actually, has anybody started on their plate tectonics lab? If you haven't, it's okay. Well, the good news is I found the actual physical, like the best file from that lab, the original copy. And so I'm thinking about printing out some extra copies because I feel like the copy I gave y'all, which is perfectly fine for most things, some of the images are kind of degraded and don't look that great. And this copy should be a lot better. So I think I'm gonna make another set of copies, which isn't too bad. I've got like 20 students, so I think I'm gonna make another set of copies and get that to y'all, so you kind of have a little bit better images to work from, and we can take our time on that. But when we get to the actual earthquake lab, you're going to be looking at seismographs like this. They have P waves, S waves, and surface waves. This is time. You can see they have 1 minute from line to line, and so this is actually a time graph here. And it's pretty interesting the way we do this. I'm not going to go too far into it today because we'll have to go into it in depth for the actual lab when it comes around. But know that your P waves and your S waves, which are the fastest, they take the shortcut and they go straight through the surface of the earth. And they spread out in a wave. This is just one particular ray path of that wave. But know that they go pretty much everywhere and pretty much anywhere. So you can put a station anywhere along the surface and still pick up the P waves and S waves. The surface waves have to go along the surface, and they're much slower. So you can see on these charts, the surface waves always come at the end. And if you're real far away, like if this is the Earth, you're probably not going to get any surface waves over here. If you do, they'll be very slight. The surface waves are what actually shake stuff. And we'll kind of get to this in a little bit. But your P waves and your S waves, generally you don't feel. The surface waves are what you feel and do the vast majority of the damage. So let's see. Primary waves, secondary waves. And let me see if I can look this up real quick. I've always told students that P and S do not stand for primary and secondary. And I stand by that. But because I think they're French terms, I don't really know what they do stand for. So let's see if I can finally put that to rest. P waves and S waves. Do we have a Wikipedia page? Let's see. Seismic waves. I trust Wikipedia. I mean, I'm not going to cite it in like a scientific article or in a paper or anything, but I trust Wikipedia. Let's see. Body waves, primary and secondary waves. Main article, P wave. Here we go. Let's see what they say about the P wave. Pressure wave. That makes sense. Primary wave is correct, but it's not what the P actually stands for. So pressure would make a lot more sense. And then they don't actually give the original discoverer of the P wave. Here. That's okay. Pressure wave sounds acceptable to me. I can go with pressure wave. And then just for my own research, pressure in French. Is it still pressure? Yeah, pretty close. Pression. Okay. Nice. And then just so I can see what's the S wave. The P wave is pressure wave. Then the S wave is a shear wave. Yes, yes, yes. That makes sense. That makes sense. Engineeringly, is that a thing? Engineeringly? Shear in French. Oh, shear. Shear. Shear translation French. Tundra. Shear. Oh, well, that's the English one. I want the French one. I would say shear in French. Word hippo. Tundra. Tundra. Okay. Anyways, yes, I was somewhat right. P and S do not stand for primary and secondary, although there's nothing wrong with remembering them that way because that does accurately describe how they come through the surface. I think they'll get to this in a second, but I'll go ahead and introduce it now. The P waves are the fastest waves. And so no matter where you're at, the P waves will get to you first. They will be the first indicator that an earthquake has happened on your seismometer. The secondary waves are like the middle waves. They're slower than the P waves, but faster than the surface waves. And so they will come in second in the race to get to your seismometer from the earthquake. And so that's why primary and secondary are commonly used. I think the pressure and shear actually is a great describer of the actual waves themselves. Because if you see, primary waves have a push-pull. And so they're going to actually push the land in the direction that the wave is moving and kind of squeeze it together. And then they pull it apart as it kind of goes forward. And so you kind of have this like forward motion like this, which accurately describes pressure. Secondary waves shake at right angles to the direction they're moving. So as they're moving this direction, they're actually shaking the ground in this direction, almost like if you had a rope and you were shaking the rope back and forth. The squiggles are going left and right, but as you shake it back and forth, the squiggles are traveling in that direction. And so those are pretty accurate descriptions for pressure and shear. Which shear means like almost like scissors. You're cutting something, you're shearing it by forcing it to separate that way. Horizontal to perpendicular. There we go. Perpendicular to the direction that you're actually cutting it. Here we go. I guess I should have just went to the next page and then you can look at it. But the pressure wave, they're using a slinky to describe that. So it compresses and it stretches as that compression and stretch travel through the surface. And so this, if you think of each coil as a molecule in a rock or in the dirt or under the surface in the mantle. This is actually what's happening to the molecule as your P wave travels through. It compresses and expands, and that compression and expansion travel as the P wave through the subsurface. For shear waves, it's the shaky rope. So you can shake the rope left and right. You're kind of looking down from above. But that left and right shake is going to travel along the rope itself until it reaches the end. And so this is more P wave. This is more S wave, which are good images to see. And then we get to surface waves. Surface waves are actually what cause all the damage. P waves and S waves will not knock your buildings down. They will not shake your house. The surface waves are what do that. And surface waves are actually really complicated. We're not going to get into all the different types of surface waves. But there are a lot of different types because there's a lot of different ways your molecules can move at the surface. And so they have like Rayleigh waves and Love waves, and they can be very complicated in their interaction. You can see that the wave is moving this way. Your wave motion is kind of circling back as it happens. And so you get this nice rolling effect. What's not nice if you're there, but a rolling effect on the surface. What is this one? They don't actually name these waves. But this is a different type where you have side-to-side motion at the surface, almost similar to a shear wave, but also you can see you have a little bit of up and down going on. But yeah, this is what will break up your roads and cause your fences to break and different stuff like that. So yeah, so the speed of travel is very different. And this is how we record earthquakes. This is actually what you're going to do in the lab. And to be fair, one of the first images you see in that lab is this image right here. They tell you to do a couple things to try to locate this earthquake. So here's what we do. Let's see. I want to see if they show you the chart or not. They give you that. Yeah. Okay. So they're going to actually go through right now how you locate an earthquake. And everybody needs to watch this because you're going to see this in the lab. And it's going to be important for you to kind of get an idea of it now. So when you see the lab, it's not as hard. You will get a readout like this, okay? The first thing you want to do is figure out your time difference in between your P wave and your S wave arrival. That is the most important. Your surface waves are generally larger, and while we could use them for stuff, if you get the time difference between the P wave and S wave, that will help you determine how far away your earthquake is. So it's on this seismograph, and usually they have it separated by minutes. So if each of these lines is 1 minute, you just go from the very beginning of your P wave to the very beginning of your S wave. How much time gap was there between the arrival of your P wave and the arrival of your S wave? So let's say this starts right in the middle at the half-minute mark here. So we're going to go half minute to half minute and just count. 1, 2, 3, 4, 5. So this is going to be about 5 minutes in between your P wave and S wave. And in a second, I'll show you what you do with that 5 minutes. It's actually maybe one of the more difficult charts that I've used and had to teach to students because it just isn't like you normally use a chart. So they talk about what are the different types of seismic waves. Your surface waves travel at the Earth's surface, and your body waves travel through the interior of the Earth's surface. Surface waves roll more from side to side. They also do pretty much all of your damage. And so what's going to damage your houses and your buildings? The surface waves. The body waves include P waves and S waves, primary and secondary, or pressure and shear waves. The P waves travel faster and push-pull. The S waves travel slower and move side to side. Now, this is how we locate earthquakes, and it's actually a little bit complicated because there's a couple things hindering us. We know that the P waves travel faster than the S waves, and the difference in arrival time is exaggerated by distance. So, for instance, let's be honest. You're in cross country. I'll use you. Andrew's faster than me, more than likely, right? I mean, let's just call it like it is. You can probably beat me in a foot race. Now, if we're racing from one side of the classroom to the other side, you're still going to beat me, but it's not going to be like by a huge amount. It's not like you're going to be all the way across the room and I'll only be halfway across the room. You'll beat me by a step or two. Now, if we go out and run a cross-country race and it's like a mile or something, you're going to have a pretty good distance on me from the finish line. So while speed is important, distance helps with that gap. On a very short race, you're going to beat me by a short amount. On a very long race, that amount is going to be longer. And the same thing happens with P waves and S waves. Over a very short distance, all your waves are going to come pretty much back to back to back. If you're measuring this from around the world, you could have several minutes of distance in between your P wave and your S wave. It just depends on your distance. So the greater interval between P wave and S wave arrival indicates a greater distance to the epicenter. And so basically, we use these seismographs to get that distance between P waves and S waves. And we use this chart here to tell us what this distance is. Now, this chart isn't like, I don't know how to put this. It's not a chart that we just like figured out. I guess it is. I don't know how to properly say this. We had to figure out this chart through experimentation. And we had to actually observe earthquakes happen, measure their times, and only after observing many earthquakes could we create a chart like this with two accurate lines. But what you have here is a P wave curve and an S wave curve. And let me grab my yardstick. And this is what you're actually going to have to do in the lab. They're going to give you this chart. You're going to have to take a ruler, and you're going to have to figure out what was the distance, the time difference between your P wave and S wave arrival. So the one that we did was 5 minutes, right? So here's how you get this information. You're going to come over here, start vertically, and you're going to slide your ruler over until you get 5 minutes distance between your P wave curve and your S wave curve in a vertical manner. Now, obviously, they show you that it's right here, but let's pretend that we don't know that right now so we can kind of see how it works. So right here, I only have what? 2 minutes distance. If I slide it over here, I'm starting in this crossover, 1, 2, 3.5, maybe 3 3/4. So I'm not up to 5 yet. I keep going over at this line. I'm about a 3/4 mark. So let's say 1, 2, 3, 4, 4.5, maybe. And so I keep going over until I feel like I'm right at 5. And you want to get as close as you can. So here, I'm pretty close to the halfway mark, maybe a little bit above it, maybe like 0.6. And so I go up 1, 2, 3, 4, 5. So now I'm to the point where I have a 5-minute difference between my P wave line and my S wave line. And once I have that, you don't want to mark it on your lab. If you do, maybe mark it in pencil so you can erase it because you don't want to have a lot of marks on here. But this tells me a lot of information. First off, you can kind of see it here. If I trace this down, it tells me how far away my station was from the earthquake that happened. And if you want to go up, they have it in miles up top. But if you go down, I trace this line down, and I see I'm roughly 3,500 miles from the earthquake itself. So that is one piece of information. If you want to go up, they have it in, kilometers. 3,500 kilometers from the earthquake itself. This would be, 2,100 miles from the earthquake. It also gives me a little bit of time information. If I trace this over from when my P wave arrived, I see that I'm getting my P wave about 6.5 minutes from when the earthquake actually happened. So it took 6.5 minutes for the waves to actually get to my station at 3,500 kilometers away. If I want to look at the S wave, it was like 11.5 minutes to get to my station from 3,500 kilometers away. Now, here's the problem. I am standing here. I have my station in Palmer, Texas, and I know that the earthquake happened 3,500 kilometers away. Where did the earthquake happen at? Can somebody tell me? No, we can't. Because what am I missing with my 3,500 kilometers?
The direction.
Yes, the direction is missing. And this is very important. So this is going to be a terrible picture, but I think it should illustrate it. Okay. Sometimes I wish I had like 4 or 5 boards. Let's see. So coming over here, putting this down. Yeah. So I'm going to draw Texas just because, this is going to be bad. And then here, get the point. Oh, that's real bad. Oh, this is terrible. Forgive me. Texans, forgive me. I had a college professor yell at a student, not yell like in a mean way, but he was presenting a poster, and he'd taken like a map of Texas, and he'd kind of like shrunk the map down, but not equally in both sides, so it was kind of squished. And he's like, listen, you may not understand this, but you can't mess with the shape of Texas. If you squish that map like that, it's really going to bug people, and they're not going to be able to pay attention to what you're saying, because Texans love the shape of Texas. You can get away with it with other states, but in Texas, you can't mess with the shape because everybody loves it. So I apologize to everyone who's bothered by this. But let's say we're here in Palmer, Texas, roundabouts, and we know that the earthquake happened 3,500 kilometers away, and this won't be accurate to scale, but I don't know which direction, right? So if I only have this one station, I can only make a circle because it literally could have been any direction for me. When the earthquake gets here, it doesn't matter what equipment I have. It's not going to tell me what direction the earthquake came from. It's just going to shake, and that's going to be it. So basically, you come out 3,500 kilometers. And actually, what I would do, there would be, just like we did with the other one, there would be a scale down here. I would take a blank piece of paper, and I would mark on my piece of paper or a ruler what is 3,500 kilometers. And I would come up here, and let's just say I did it this way, and it's 5 inches. So 3,500 kilometers is 5 inches. I would start out in one direction, and then I would literally just turn it a little bit, do another 5 inches. Turn it a little bit, do another 5 inches. And I'm going to go all the way around and just kind of make these tick marks. And that's going to show me where my earthquake happened. And when I get done, I can draw the line in between all the little dotted lines. And basically, I will have, that's not too bad. I will have a 3,500 kilometer circle in every single direction from where this happened. So this is a problem. I still don't know where the earthquake happened. I have a line 3,500 kilometers away from me that I know it probably took place on that line, but where on that line, I have no idea. Now, what if I had another one? What if I had another seismometer somewhere else? Let's say we had one over here in the Panhandle, and theirs was like 2,000 miles away. From the earthquake was 2,000 miles away from their seismic station. So they do like a 2,000 mile line. They would measure it out here. Let's say it's right here. I don't know if these are accurate to scale, but they do their like dotted lines out here, and they make their circle. Now, and they don't even have to do it all the way around because we've discovered something new. If I know the earthquake happened on my line, and they know the earthquake happened on their line, the only place the earthquake could happen would be where our two lines meet. And so that's two places, one of two places, right here or right here. And so now we've got it narrowed down. Instead of being literally almost anywhere, I have two exact locations. And something amazing happens if you add a third station. If you add a third station, let's say it's down here in El Paso-ish, and theirs is further away. They do their measurement, and it's like all the way out here to 4,000. This is going to be rough because I'm not great at drawing. But they're going to do their circle. It's going to come around here. And if you have 3 stations, you should only have 1 point where all 3 lines meet. That is where your earthquake happened. So now we've eliminated this one over here because the third line doesn't meet that. And so what this is called is triangulation. If you have 3 points, you can figure out exactly where your earthquake took place. It's where all 3 distance lines actually meet together. And so you're going to have to do that on the lab, which again will be a little while from now. We're not going to rush this one, but they're showing this to you in the PowerPoint, so I wanted to kind of go over it. They're always going to give you 3 stations like this. So you're going to take your distances between your P waves and S waves. We have Nagpur, India. We have Darwin, Australia, and we have Paris, France. We're going to get our 3 time differences between our P waves and our S waves. India is 1, 2, 3, 4, 5 minutes, which we've already done. Australia is going to be 1, 2, 3, 4, 5, 6, 7 minutes. And then France is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe like 10 and a half. And so we're going to take those 3 measurements. We're going to come to this chart. We're going to find the differences between the P waves and the S waves, which gives us our distance from the earthquake. And then you're going to come to the globe, the actual map or globe that they give you, and you're going to start with individual spaces, individual seismographs. So we have the India one. We're going to draw our time distance from India, not our time distance, our distance to the epicenter from India, make our circle, 3,400 kilometers. They do the same thing with Darwin. They make their circle. They do the same thing with Paris, France. They make their circle, which is 8,200 kilometers. That's a pretty big one. And then when you get done with all 3, there's only one place that all 3 of the circles meet. That's where your earthquake actually happened, which looks like it was up in China. China has a lot of earthquakes. They've got a lot of activity going on up there, earthquake-wise. So, yeah, nice. That's a nice illustration of how we find earthquakes. And you're going to do that in the lab, which is actually going to be pretty fun, I think. My personal opinion. How are seismographs used to locate the earthquake epicenter? You find the difference between the P wave and the S wave. You look on the chart to actually get the distance that your seismometer was from the epicenter. And then you have to have at least 3 seismographs to triangulate the epicenter. If you have more, that would just help you get a little bit more accurately. Because everything's, the way waves travel through the surface of the earth isn't idyllic. It depending on whether it's traveling through water or different types of rock can have different types of speed. It's not always going to go the same speed all the way throughout the earth. That's just kind of like an average. So, the more stuff you have, the more accurately you can get it. So let's see. Determining the size of an earthquake. How much shaking is happening, how much damage is happening. So intensity, we're going to have some different terms now. Earthquake intensity measures the amount of ground shaking based on property damage. So how much ground shaking happened. If we don't have something there to actually like fully record it in a meaningful way, which it's hard to get something everywhere where you're going to be able to pick that up. The best way to look at it is by how much stuff it destroyed. If it destroyed a lot of stuff, it probably shook pretty hard. If it didn't destroy anything, then it probably didn't shake very hard at all. So we use historical records for things that were way back in the past, and we kind of do it the same way. This is really the same way that we do tornadoes. If you look at the F scale on tornadoes, it's based loosely on wind speed, but they go in and assess the damage. How wide is the path of damage? How long is the path of damage? And that's how they get their F scale on tornadoes. So kind of the same thing for earthquakes. We have a couple different scales. We're more familiar with the Richter scale, but we're going to start with the modified Mercalli intensity scale, which was developed in California in 1902. And actually, I think they'll give some details on that in a second. But the modified Mercalli intensity scale talks about intensity, which is your actual shaking based on property damage. The magnitude, which is the Richter scale, the magnitude is a quantitative measurement of energy released. And so this is actually, they should be similar. The more energy released, the more damage you should have. But if you have an earthquake that's underwater or in a very remote, isolated area, possibly like different areas of China, you may not have as much damage that's visible. And so you hopefully can figure out actually how much energy was released. So we use the Richter scale for that. It's related to amplitude of the largest seismic wave. So we see how much the waves are actually traveling up and down, what their magnitude is, which should equate to the energy released at the moment that the earthquake happened. We also have moment magnitude, which measures the total energy released based on the amount of slide, area of the rupture, and strength of the faulted block. So they actually look at what, probably with GPS pictures or images, they look at the area before the earthquake and then after the earthquake and see how much it actually moved along the fault line, which should tell them, if they know the strength of the rock, how much energy was released, which takes a lot longer to actually get done. Richter scale you can get almost instantly because the seismic waves come and you can do that calculation quickly. Moment magnitude would probably take a lot longer to actually get correctly. So we're not going to go through all this, but know that the modified Mercalli intensity scale is a little complicated. Everybody look at this. They have, 12 different ratings in a way, and it goes from not felt except by very few under especially favorable circumstances. So really small earthquake, not really a lot of damage, not much going on, to a 12 scale, which is damages total, waves seen on ground surfaces. So literally if you're standing outside, you see the ground like moving like a cartoon. And then objects thrown upward into the air. So not just like buildings broke, but like your car gets tossed into the air by the giant waves. And so this is very, very extreme. This is very, 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 very not extreme. It's very, light earthquake? I don't know. I lost my words for a second. And they have everything in between. So this is all based on damage, which is your intensity. So that's your modified Mercalli scale. I'm not going to go through all of them. I don't know that they have a whole bunch of questions on them, but it should be in your book if you do see some homework or some test questions on it. So determining the size of an earthquake. This is magnitude. Is this the Richter scale? Average per year? No, I don't think this is directly related to the Richter scale. But I'd like to point out, I don't know if I've kind of mentioned this yet because we haven't gotten into our damage stuff. There is a relationship between how bad something is and how often it happens. And this relationship exists in almost every area that we look at naturally. So whether you're talking about volcanoes, hurricanes, mudslides, earthquakes, fires, whatever it is, there's this like inverse relationship between how often it happens and how bad it is. So like fires, they're little fires that happen all the time. Grass fires, field fires, fires set by humans. They happen every single day. There's a fire department in every single town because this kind of stuff happens. Giant fires that cover hundreds of thousands of acres and destroy thousands of homes and kill a lot of people don't happen that often. Same thing goes with volcanoes and hurricanes and earthquakes. There's literally hundreds of earthquakes that happen in this country every single day. They're very small. They're very shallow. They don't do any damage, and they happen all the time. Your bigger earthquakes do not happen all the time. So that's what they're showing you here. Down here, let's just say this is the magnitude. This could be Richter scale. It doesn't say that, but let's just imagine it's a Richter scale. So if you have below 2, which isn't really felt by humans at all, generally not felt by humans, but maybe recorded, you're going to have an average per year of well over 1 million, probably 2, 3, 4, 5 million. It's just hard to know because we don't even pick up very much of them. What is this? Energy release? Not very much energy. 56, equivalent of kilograms of explosive. That's not a very good equivalent. Are we all familiar with the explosion of kilograms of explosives? Yeah, maybe we should have picked something a little bit better to compare that to. But only 56 kilograms of explosions on a small one. But note, as you go up and they get bigger and bigger and bigger, the numbers get smaller. So if you're in between a 2 and a 3 on the Richter scale, we have about over 1 million of those every year. If you're in between a 3 and a 4, we have only 130,000 of those every year. In between a 4 and a 5, 13,000. And it just keeps going up and up and up on the magnitude, but you get fewer and fewer of them to where you get up to like above a 9, in between 9 and 10. Those happen less than once a year, sometimes rarely, and they show you some examples here. Chile, 1960, Alaska, 1964, Japan, 2011. So not even like every year, sometimes not even every decade. A lot of energy is released. It takes a long time to build that up, and so it's just a lot less likely to happen. And so this kind of like inverse relationship of how bad something is versus how often it happens kind of works for everything. Like the absolute worst hurricanes just don't happen every single year. They take I don't know why, because they could happen every single year. There's nothing about it that could keep it from happening, but they don't. We have normal storms that aren't that bad that happen like every single week somewhere in this country. And just for an example, and then I'll probably stop for the day because I want to. Yeah, and it's almost time to go. Let me go over here and show you something on the interwebs. So, the United States is good about, what is this? Oh, yeah. It's good about giving you information. So, if you go to the USGS, which is the U.S. Geological Society. Oh, I didn't even have to click on it. Right here, I just searched USGS, and the first thing underneath, like sub-link underneath their website, latest earthquakes. Click on the latest earthquakes. They will show you earthquakes that happened, let's say the 20th, literally today. Everything on this list happened today. you got to go down quite a bit to get to yesterday. So today we've had a 4.3 in Alaska. Can I open this up a little bit more? Guess not. Can't move that over. But it looks like a 4.3 in Alaska, 3.9 in Alaska, a 3.0 in Idaho. And it looks like the rest are Alaska. What is this? Hawaiian Napu? Napupu, Hawaii. Hanau, Napupu. Never heard of that place, but it's in Hawaii. So earthquakes happen all the time. Here's one in California, a 3.4, and then a bunch in Alaska. Here's one in Nevada. Yeah, earthquakes all the time happening. You never know when one could strike. They'll get you. Welcome. Yeah, what were you just standing in the hall?
Yeah.
Do you have late arrival?
And I came here.
Have a nice day, everybody. Have a nice day.
I'm so
Have a nice day, online people, including those of y'all in quarantine. Bye bye.